Start recording. Alrighty. So last time, we've got this funky situation. We've got a box, and we draw some axes, and we've got these blue lines here that are projecting the circle onto each axis, from which we're deriving this thing. And where we left off last time is we were doing this bit of algebra. So I'm just going to whiteboard this for a brief while so we can finish that off. So we've got the origin, and we've got well, we have two shapes. Let's say we have a shape here, and it's we'll just go horizontal axis, I guess, and we have, say, a shape here, and then we have an arrow pointing out this way that brings with it an axis. So this is basically the diagram we have. Now, so hopefully this makes sense that this is the axis A.
Yep.
Now, if you recall, the thing about this axis is if I have like I guess this is what we're going for, is we're going for this segment on the axis that's, we start at the center, we project the center up onto the axis, and then we just go out radius in either direction to get that. So hopefully that makes sense. What you should recall is that this axis, and everything on it, is one-dimensional, so it's pretty much free to move up and down perpendicular to itself. So this has the same meaning as this, has the same meaning as this, has the same meaning as this. Hopefully that rain isn't too loud on the recording. So that makes sense so far?
Yep.
Excellent. All right, so I'll just undo all that. So the way that we derive this diagram here, so this axis here, is we take this A, this axis vector, in fact it's A hat, and it's a unit length vector. So really I've just drawn it translated over, the arrow translated over here. What it really is like this vector here, and it produces an axis like this. So still making sense?
Because obviously it was A hat before you wrote A hat, right? When you wrote A, this is the axis A that we happen to be drawing. It was A hat before, so we're just talking like the axis is just this direction, like the fact that it's this particular one is they're all going to be one-dimensional, right? But this particular one just happens to be going in this 90-degree angle.
Exactly. So I could have a different axis. Like I could have an axis going out there.
Right, but it's still unit length though.
Yes. So and the reason it's unit length, if you recall, our projection formula was something along the lines of A hat dot B is projection. And you recall we also had a different formula equals A dot B divided by A length. So these are equivalent.
Right.
Because you obviously divide by the length to get a unit length vector. So all I've done is I've just drawn the arrow here. So I've actually, this is not particularly meaningful. Oh, that was a mistake. Because this is a vector. It's got an x and it's got a y, and that's it. So hopefully it makes sense.
Yeah, that's right. I mean, it took longer last time because we were just like I was having trouble with the translating the position, you know, especially for the circle and so on. But yeah, I totally understand that we're talking about a 1D, but like this axis isn't anywhere. We just happened to draw it there and we had to deal with the translation. But yeah, it's not really anywhere. It's wherever you want it to be. It's conceptually.
Okay. Yep. So we have this position B that's we're going to project eventually, and obviously this is in world space, so it's all relative to this origin. So this is actually a vector B there, and when we do projection of B onto A, so if we do PRJ equals A hat dot B, we end up with the distance from here to here.
Right.
And so hopefully that makes sense. So what we want to do then, and this is kind of just for practice and visuals, because eventually, because it doesn't matter, where we're drawing the axis, we won't actually have to worry about this. But for drawing it, we actually need to care. So we have this distance here. And so we could just draw this sort of slightly more reddish orange line here, but we want to draw this more orangey orange one here. And so if we tried to do it just straight off here, and you remember we accidentally did this last time, we end up with an orange line that far away from here, if we just do the straight up translation. So
right.
That following so far?
Yeah.
So all we need to do is we just need to sort of, I guess, project, let's pick a different color. Sorry, no, this is not A. Let's call this, because that's the axis. We'll call this position C. It's going to be this one. So we need to project C up to here, and this gives us this distance there.
Yeah, that's the part I think that it confused me last time about that we were actually I thought we were just going to slide the orangey bit down, but in fact we were going to project up from, in this case, C up to the origin line.
So we have, what do we call that? We go projection of C, and I guess the other one would be projection of B. So what we can do then, and hopefully this is the bit of algebra that I was doing before, and just sort of restated geometrically, and that is if we go from C and we subtract, basically go backwards by this amount, we end up here. So, and hopefully that makes sense.
Yep.
And yeah, and you'll notice that is that shape we've produced by going backwards from C to by PC.
Yeah, okay, because yeah, I'll take your word for it. Well, yeah, no, okay, no, I'm okay. Yep, sorry.
Yep, no, that's all right. So basically, to finish up, then we use that pattern that we came up with. So if we want to have this position here, for example, we have, like, this is a distance, this is not a vector. But if we want this as a vector, all we have to do is this pattern. It's C plus, well, in this case, minus, because it's a negative, minus PC times A hat is this position here. So hopefully this one makes sense.
Yes. Well, sorry. The only thing that I thought that PC was already in A space and therefore wouldn't need to be
Okay. So
scaled by A again.
Let me redraw that a little bit clearer. Okay, so this point here is C, which is a vector, minus PC, which is a scalar, multiplied by A hat, which is a unit length vector.
Sorry. Yes, of course. You have to. That's how you get it into this. That's how you get it back to a vector, so you can actually express it properly, because the other side is considered that, because the other side is already a projection onto A. So you need to make the scalar project onto A also to even out the equation, right?
Mm-hmm.
Okay.
So,
gotcha.
Then finally, if we want this position, we have this PB length, which is all the way from here to here. So if this is the point we want, then we just add on PB times A hat. So that should be pretty obvious. Yep. So now this is the formula we ended up with.
PB times A hat, that is the orangey orange line, is it not?
Pretty much. So, like, strictly speaking, let's draw it in magenta. It would be the vector that runs there.
But you're multiplying it by A hat, not the origin. Isn't what space is the origin line in the magenta line?
Well, that's in I guess world space. So
right.
It's all relative to the origin. That's why I draw it like that. Like, yes, it is this vector, but if I draw it in its sort of in world space, it lands here.
Okay, yeah, I'm with you now.
So if I were to sort of follow this whole thing along, I'm start at the origin because I've got nothing, and then I'm going to add C to it. So I go all the way to the C, and then I'm going to subtract PC times A hat. So I'm going to go back here, and then I'm going to add P times A hat. So I'm going to go all the way there. Perfect. And that's how I end up to that at that point. So
awesome.
Okay. So all we want to do now is let's make our lives a bit easier, because we're going to be drawing a whole lot of stuff on this axis. We're going to be drawing, this projection, and then we've got another one that's like going to be the other shape. I guess C is a shape. We probably want to project it onto the axis as well. So we're going to want to draw a whole lot of projections onto this axis. And they're all going to basically be of this form, and this is the only thing that we're actually changing. And does it make sense why that's the case? So for example, in here, if we want like this point and this point, we're going to take some distance in like minus radius and plus radius.
Yeah. No. Okay. Yeah. Yeah. Okay. But all you're talking about right now is getting that line, so that's the only position that matters. That's what you're saying.
Well, we want a form that will let us put a whole lot of positions onto this line, and they're all going to be relative to this point here, because we've just taken this axis and moved it up and down.
Got it. Yeah. So yeah, in this case, in the pattern, PB is basically X, and you want to fill that in with whatever point you're trying to map to the line.
Exactly. So basically what we're going to do is we're going to take this whole thing, and I mean, it's going to be Q plus, I guess, x, a hat, whatever x is.
Yeah, we did this last time.
Yep. So now we're sort of we've reached the point where we were at last time, and sort of work it through geometrically. So hopefully this is making sense. So this is now q, and we can have a reusable formula that we can just slap this into. Okay. So let's just finish up the algebra so we have this in a nice format. So you can see here, this is, we've got this thing here. So I'm going to just get rid of this axis space, axis transform. Okay, so this is going to be, this is minus that projection times the axis, and we're starting from the axis base. Minus that is the axis 0.
Axis base is q, so you just basically
axis 0 is q.
Oh.
Axis base will be c in our diagram.
Yeah. Okay. Yep.
So that's just going to be our starting point, and then we're just going to be like axis 0, and then we can get rid of like this axis transform thing. And this just simplifies all of these. I can get rid of axis transform. And they all just base off axis 0. So, do you want to catch up that bit of code? And
sure.
Then we'll start adding some bits.
Yep. Okay. Faster than you just want me to go.
Sorry.
Oh, sorry. I'm talking to myself. You don't have to worry about.
All right. It's raining pretty hard here, so hopefully that's not coming through too much.
No, it's pretty relaxing actually. Pretty zen. And then make sure I think I'm missing something in the arrow. This is axis 0. Axis. I think that's it.
So I just need to get rid of axis transform on this one.
Oh yeah.
And yeah, so in theory that should produce the same diagram, but this is going to make our lives much easier when we start adding more stuff.
Yeah, looks good.
Excellent. Okay, so let's start bringing in some other code. I'm just going to have a quick read of these notes. Okay, so I don't think we need to actually draw this circle projection, so I'm just going to delete this aqua line. And then I'm going to go up to the rectangle projection thing. So this is just above this code, and this is where we're projecting a rectangle onto an arbitrary axis. So just that, and I'm going to bring that down below the arrow here. So while you copy that, I'll just run this so we can remember what this does. So this is this code we did a few weeks ago. So grab it and stick it in here. Now we've got a small problem here, and that is we've actually got min and max twice. So what we might do, and because I know this from working ahead, we will actually need both of them at the same time, so we can't just slap it into a scope. When I was testing this, I did the same thing, and then I had to back it out. So I'm predicting the future here, and I'm going to call this one A start, and this one A end, and this one B start, and this one B end. And I can do that because I know where this is going. So I'm going to keep powering through this, so just stop me if you want a more detailed explanation of any of this. So what I'm going to do is I'm going to look at this and be like, okay, this should look really familiar because it's almost the same as this. But obviously what we've added in this case is we're now, the axis isn't around the origin, it's around axis 0. So we're just going to just copy that in there. And now we've got our new drawing form, you know, that times the axis times the scalar. And in theory, this should just straight up run. So let's give that a go. I've got the old code on. Good grief. So it makes quite a fun diagram.
Clear as mud.
We might go in and we might change the colors perhaps. Let's make that one a bit less bright, and we'll call this one, how about green for the square, and we'll reduce the opacity a bit as well. So if we run this, it looks like our axis projections are correct. The green and the red arrows seem to be at the right spot, and like if you take a look at that, are you happily convinced that they are essentially correct?
I'm a little, yeah. I get well, the red, yeah, except that we don't have like, we only got one direction on the red radius-based arrows, which who cares, I guess, but it kind of doesn't make a whole lot. Like you almost want to, like in your other layout, you've got them end capped with lines. In this case, we've got one arrowhead, but otherwise, yeah, they seem like they're in the right place.
Well, let's fix up these other lines because clearly something's gone wrong, and I think what's gone wrong is we've forgotten to add axis 0 to this as well.
Oh yeah.
This might work a little better. This should hopefully, yes. Now that, I mean, it's still a messy diagram, but
hopefully at least it looks geometrically sound this time.
Yes, like you can see that, you know, this top left one, it projects onto this axis at 90 degrees, and you get the top of this green one, bottom of this green one, and so on.
Yeah, that looks good to me.
So hopefully that's now making sense. And what were you saying about the arrowheads before?
The red arrows, the ones that are, those that represent the radius, like the number line for the circle's spot on the axis. In your diagram, they've got end caps, like 2 lines, and kind of, okay, that's my number line. And then on this one, we've got one arrowhead on one side, which threw me off for about a second, but otherwise, it's probably fine. We could put an arrow on the other side, but we end up making 2 draw calls probably.
I'm not sure I'm understanding what you mean.
Okay, well, go back to your. I mean, this is super minor, so it's almost not worth mentioning. If you go back to your layout.
This one?
Yeah, anyone. Yeah, so the orange lines have got bars on the end.
Oh, okay.
And in ours, we have like one arrowhead, which kind of was like, well, what are we communicating there? Because here we're not communicating a direction, and the other one is communicating a direction.
So this is going to become important very soon, in fact. So what happens is when we go to do the we've just got a one-dimensional line, and we've got two overlapping or potentially overlapping segments on it, like this. When we go to do the intersection test, we can save a whole bunch of compares if we know for a fact that basically this is a situation that the axis is pointing in that direction, and we have the min and we have the max.
I kind of figured that was the case. I just
Yeah.
yeah.
So
Just because that's the way it's always been, that where direction is mattered, because we're doing everything carefully so that the number line is always going one way, so that we can, for each or whatever, or enumerate the arrays of the circles and the shapes and only think about basically one half of the world, I guess, in that sense.
I guess yeah. Like, I mean, that's one way to think about it. Is, I mean, it would be valid. Like, there could be a thing over in the negative side of this axis, and in fact you'll find there is. If we look here, like this axis going up and down, it starts at the origin up here, and we're actually behind, so this will be, that number will be negative, but it's still pointing in this direction.
Okay.
Yeah. So basically, what you find, if you didn't have this situation, you'd basically have to do like a compare later on in the algorithm to effectively sort these two and flip them around to do the rest of the intersection test.
I don't want to get off track too much, but does this have anything to do with so-called, what we might call like a two-phase or a full-phase update? In other words, this the example offhand is like two characters in a game are gonna punch each other, and they both punch each other at exactly the same time, and in like most of the time in most naive engines and probably even RCRU, the character who happens to be in the actor list ahead of the other one would end up winning that particular overlap test because they hit the other person first. But in reality, you'd have to sort them, or a more sophisticated way would be to have to check the loop twice, basically, to sort that out. And I don't know if that's completely, does that have anything to do with the fact that we're trying to do this with one direction, or is that this is purely a geometrical idea that we're using?
This one's a geometrical idea. So this is just feeding into how do we tell if these lines are overlapping. The order of the lines themselves doesn't particularly matter.
Okay.
So we do something like that over here. If you recall, when we do our do separation method, we have this pending separation list. And so you recall the reason we did that is so that we are not moving something and then testing for intersections and then moving something else and then testing for intersections on things that come after it in the list. We're doing all of the tests, working out all of the separations, and then applying them in the next phase.
Right, and I guess that's kind of what I like am accidentally and incorrectly intuiting about it, is like you're doing all of the overlap checks in advance in this batch so that you don't do something later that's that would make it inaccurate, which would be the same thing as that punch test, in the sense that you have to check all of the overlaps, including the second character's overlap, to see who won the punch fight, because in that case they both won. But anyway, I'm just kind of flailing.
No.
There, but okay,
like that.
Good enough. They're just separate ideas.
It's correct. It's a separate idea. I mean, we can, if I can find it. If we bring this one in, I'm trying to think whether it's in there and exactly where it is. It will be in the physics section, which is in I don't suppose you recall where physics is. It's over here.
Yeah, it's in engine. Anything that wasn't in the rudimentary objects is in engine. I don't think I think that could be a whole new project, but I haven't talked to you about that yet. But that's a different thing. I think character. Well, character physics is. Yeah, I think you might find this in code that's not here. Most likely it's in character.
If you're thinking of the thing that I'm thinking of, no, I'm looking for the thing. So there's a thing that I wanted to show you in the physics engine,
Okay.
and it's world physics. It's world physics, and I think it's world physics. And what it does is it collects all of the it's not character physics. I think it's world physics. Yeah, okay. So, and you recall we have a method on actor. If I can find actor real quick.
That's also in the engine.
Yeah, actor.
Top level. Yeah.
So we have this method register physics, and what this does is it's a little bit cobbled together because we basically have both systems working in the engine. We try as much as possible to do things in an order independent way, but some of the stuff we don't. For example, actor.update, like anything that happens in update and the state update method, that happens in the order of the actors in the actor list.
That's right.
But physics, in particular, that becomes a real problem, which is why we've added this register physics to the system. And what this does is it goes into the update context physics. So this is the physics information for the frame, and it adds the actor to the physics list. And this
right, which is a lot more like the overlap check in the shapes code that doesn't want to do anything wrong, so it does everything in advance.
Yes, and it's a lot like this pending separation. In fact, it's a bit of the reverse of the pending separation because the way it works is we can move the actor itself. So the actor's got actor.position. And in the update method, you can move this around and all sorts of things. But over here in world physics, when you want to query the physics state, you actually don't ask the actor for the physics. You're actually asking, you're asking one of these collision queries. Get me where's the ground for this frame, and it tells you where the ground is. And it doesn't go through the actor list. It actually goes through and tells you all of the actors that we've pre-registered, and uses the position at the start of the frame rather than the modified one.
That makes a lot of sense.
So
it almost has a cache coherency flavor to it too, because you're kind of like lining up things. Like even though there's actors all over the place, you're really just talking about these are the ones that I've registered for physics. These are the ones.
Absolutely. That would we talked about that a fair bit last time, and that's exactly what's going on here. That's why there's here's whether the collider is static. This one is sort of the really important one, is the bounds X. Because we're not doing any spatial partitioning, we need to basically go through all of the actors very quickly and find whether they're relevant to the test. So we check their X position because obviously the levels are a lot wider than they are tall or deep. And so
right. So world physics is becoming very structive array-ish in that sense because you can see all the different buckets of
exactly. So
slivers.
So there's this bounds X array, and that's like as tightly packed as possible. It could be tighter, but that's always the case. And so there's like all these entries, and it's basically X start, X end, X start, X end, X start, X end, And so every time we go and do a collision check, we're basically asking the physics system which actors are relevant, and it's going to go and grab, because it's such a small thing, it's going to grab cache lines at a time. It's going to grab that, and then it's going to grab that, and it's probably going to prefetch this, and so it's very quickly going through this loop. And I'll show you the loop, and this is why this is in a very specific order. Conditions are checked in this order to improve cache behavior. So we reject the ones that are static or not static. We do this early, I think for reasons. But then we go and check. So static only. So this, if static only is a parameter to the method. So this is going to be branch predicted away, hopefully, in the cases where it's not relevant. So most of the time this will be off. So most of the time this code won't happen. But then we go here and we're like, all right, is the thing that we're looking for inside the bounds that we're looking? And we're doing this very quickly. So this loop here, even though it's like got all of this maths in, and we're querying height maps, and we're checking a list of ignored entries and so on, almost everything that's not relevant is just going loop around, loop around, loop around. And so that's how we get through the 100 odd physics actors in the game, because most of them are spread out and not relevant. So does that make sense?
Yeah, absolutely. Sorry to derail the conversation, but that's really helpful to know.
No, I mean, derailing is how we learn things. And so you'll notice that like there's every single physics query has this structure at the top, and it's like rejecting as many things as possible before we actually do any actual physics calculations.
It's like the numerator concept, except without all of the internal junk allocation.
So let's pop up the stack a little bit and get back to what we were doing. So we've got all this, this clearly amazing diagram. I might just, I might just pull out, I'll comment this out for now, because we don't really need that many arrows on screen. We'll get rid of all these like little ones. So we've just got our projection, because we've now satisfied that these are the correct projection lines, so we don't need those little guides on them. And then we made an intersection test. So let's go and grab that. It's up in do separation, and this should look nice and familiar. So this bit of code here. So do you want to just copy that one down?
Yeah.
And so you'll notice that X and Y are the same.
Oh yeah.
So take your pick. And we'll just copy that into our drawing. And so, I mean, you'll recall that sort of what we're going for here is similar to this diagram. So we've figured out what the separation is, and we've done the separation on the two shapes, basically. So we're going to do basically that, but for two different shapes now. So this is checking whether they overlap, and this is where the end is greater than a start comes into play. Because if end could be less than the start, then we'd have to stick another couple of conditions in here to make that particular bit of logic work.
Right.
So all we're going to do is we're like, all right, separation A is that, separation B is that. If A is the smaller one, we'll use the negative of A. And if B is the smaller one, we'll use B as the separation. And then we have this did intersect thing. So just to make life easy, I'm going to go up here and be like, all right, cool, did. Sorry, that's true. So that's just the code from before. So we'll solve that one for now. We'll come back to that in a sec. So what we want to do is we want to draw the separation, and let's draw out what this should look like. So we have go back to my other layer. All right, we have a green arrow, and we have a red arrow, and we want to draw this purple arrow. But the thing is, we could also have a red arrow and a green arrow, and then in that case we want to draw this purple arrow, which is between different things. So hopefully this looks familiar because we've done this already.
Yep.
So those are the two conditions. So we have, and this is why there's that negative sign in the condition there. So this is a start. Let's subscript that. A start to B end, assuming B is this green one, and this is B start to A end. And so all we have to do is just draw those arrows. So let's grab some code for drawing arrows. This one will do. Expand those out. I'll comment out that for now. So this is the case where A is smaller, so separation A is smaller, and that's what we want, but we want the negative of it. So we're going, now this pattern here should look really familiar at this point. This is getting the vector that goes from end minus start. So this is the vector from A start to B end.
Right.
And because we're taking the negative, we're effectively reversing these two terms. So the negative is going to be there, and that's going to be a positive. So this is, in fact, once we negate it, that's the vector from so it was the vector from B end to A. Oh, Jesus Christ. This is always confusing. We start at A start and we go to B end, and then when we negate it, we're going from B end to A start. So we're going from B end to A start. And then in this case, this is the other case. This is this one, and we're going from A end to B start.
A end to B start.
Now, 50-50 odds that I've got those mixed up. But we'll...
oh, you made it. Oops, you made it purple. I didn't make mine purple.
Well, purple will probably, in fact, nice, more opaque. This will probably help a little bit so we can actually see what we've got. So already I feel like I have something backwards. Fortunately, well, I wouldn't say fortunately, but I've got them consistently backwards at least.
You've got way more arrows than me too. I've got like this one.
Well, that's because this is the intersection test, so only the axes that overlap are going to have this purple here. I'm just going to fix up the order here. A start to B and P. I don't know why I got this wrong because it's literally written in my notes, but that's the sort of, and you start to learn what kind of errors you make all the time. Like, I just know that this sort of reversal error is something that I'm very prone to making. So this is why drawing out these diagrams helps, is because you immediately is like, the arrow is facing totally the wrong way. So yeah, hopefully this diagram makes sense now.
Sure. I mean, mine is different because I guess my thickness is just way different than yours.
Yeah, I think your thickness is different, perhaps. Also, you've put the shapes in different positions. So, like if I put
there's
that there,
yeah.
that's looking a bit closer. Something a bit more square, and that. What I could do we have a perpendicular? I mean, we could lower the opacity of this thing, and then we can actually see through it a bit. And so the idea is basically, whoops. The idea is basically that the purple is where the red and the green arrows overlap. So basically, so one way we can, so I basically just want you to be satisfied that that's the case. So one way you can tell that is if you just draw the square and the circle next to each other and just focus on this single axis, for example.
Yeah, that's a good idea. We did that last time. It was helpful.
Oh, I mean, in fact, we can stick in we can just turn off the other axis. So if I is not equal to, I think what is it? Unit x. So if I is not equal to 5, continue. So I've got this single axis, and hopefully you can see that the purple arrow is where they overlap.
Yeah, and I mean I can see it on mine. Mine's noisier, but I can see it on mine too.
Yep, excellent. So, I'm looking at yours.
I'm a bit confused by the directionality of the arrows. Like the arrowheads are kind of everywhere. I'll just trust that that's okay.
Well, hopefully, if we've done this correctly, the arrowheads should be pointing along this axis. I think. Let me double check this is right. Oh. Sorry, just bear with me while I confuse myself.
I don't like this arrow here.
This purple one here. Yeah, I feel like you've got an error in your thing because this one here also appears to be wrong.
Yeah. Okay.
But I feel like I have. Remember when I said we should reverse these things? Perhaps I was wrong about that. Because the arrows should be showing the separation from. Yeah, I've made a small error. I think I was actually right the first time. A start, and this should be B start A end. Yeah, so this one is, yeah, okay.
B end, A start, and then A start, or B start and A end. Yeah, okay. Yeah. No, this looks almost exactly the same. Oh, maybe this one's different, but hold on a second. I'm not sure what this arrow represents. So, here, because I'm looking for, like, I know I can see this part and I just can't see.
Let me turn on mine, but I think we'll have to do a little bit of debugging, which is always helpful. So yeah, you can see that there's problems in your diagram. So I'll just draw this circle again. So possibly I have a bug in my code too. No. I think this is correct.
Much better now.
That's gorgeous. Okay. So I misspoke. I misspoke. We aren't actually getting precisely the overlap between those two arrows. We could get that. I mean, that's an option. But in the case where, yeah, I know exactly what we've done. I think the O just sort of signals to me that you've just figured out what we've done too, and that is, if you recall, we actually have 4 cases here. We have the case
That's
where the
right.
red arrow, yeah, exactly.
It's the corners, right? Oh, sorry, I could be wrong, but I was thinking about how it looks wrong to me, but isn't, because of the fact that we have the 4 corners of the rectangle. We also have the 2 axes from the circle, because when we test these, the shorter distance can be like in between the 2, right? Like in the corners. I remember the first diagram you drew.
No, because we're testing all 6 axes here, so we're always testing the corners, at least for this diagram, and we're testing the rectangles, axis orthogonal axes, the x and y axis. So what I said, which was wrong, was it's where they overlap, and that's the case here. But in the case here, it's not correct to say that it's their overlap. That what I said was wrong, and what the diagram is showing us is correct. What it is, in fact, is it is the minimum separation distance. So it's how far do we have to move this point to get it outside the thing.
Okay, yeah.
So that's why you're seeing that in your diagram. It's because this green section in this case is entirely contained within the red section. So hopefully that makes sense.
Yeah. Okay. Yeah, I was way off, but I get it.
Yep. Okay. So we have this now, and you can see, for example, like this axis here, where they don't one is not contained in the other, then it is in fact the overlap, and that's going to be the separation amount. And the reason the arrow is pointing in that direction is because this is the amount, and you hopefully recall this. This is the amount we want to move the rectangle to separate it from the circle on that axis.
Mm-hmm.
And you recall, so we have this thing where the order of these 2 things is quite important. So we're just about done here, so let's finish up. We copied in this separation code where we were fetching out the separation by axis. Actually, maybe we will hold this for next time, because we're at the hour. How are you feeling?
I'm good to call it. I don't mind a little leaking into the next session. It's up to you, but
I think we'll call it, because then we can actually dive a bit deeper into this next section and discuss it, the implications and stuff in more detail. So I think that's probably a good time to stop. So we've got all the axes, and what we want to do next time is basically find out, did we intersect or not, and whether or not we intersected, we will figure out how much to separate by based on the smallest separation distance. So we'll find the smallest one, we'll separate by that amount, and we'll have the same thing as the circle. So let's close off OBS. Thanks for watching, everyone.